So now that we talked about a vector times a scalar, we're going to talk about multiplying vectors together. And there's actually two ways in which we can multiply vectors. There's one called a cross product, and another one called a dot product. And we're going to start with a cross product first. Now, cross product is probably the more complicated out of all my vector multiplication, okay? Because when you multiply things using a cross product, you multiply one vector and another vector together, but you use that simple multiplication sign. But because there's actually, when you're talking about vector multiplication, there's two symbols that we use for multiplication, for products. The first one is this symbol, which we use entirely for cross products, and the other one is going to be a simple dot, and we use that one for dot products, okay? And both of them lead to two completely different results, okay? As a matter of fact, the cross product creates a third vector. So when I multiply one vector cross another vector, I end up getting a third vector out of that. Where the dot product, if I have one vector dotted with another vector, I end up with a scalar. Okay? Cool? So vector crossing with another vector gives me a vector. Vector dotted with another vector gives me a scalar. All right, now let's do what a vector cross product should look like. Now, vector cross products are pretty interesting because what you're trying to do when it comes to vector cross products is you're trying to take components of vectors that are at right angles to each other and multiplying them together. Okay, so in this case, let's say I have a vector A and a vector B. Now we can pretend whatever kind of vectors those are, be forces, they could be radiuses, they can be whatever they need to be. I use force and radius because that turns out to be torque. A nice cross product. So vector A times vector B. Now, if it's in a perfect situation, if A and B are already 90 degrees from each other, then the result of A crossed with B is going to be equal to AB. Okay? Now, there is a direction associated with that vector AB. Okay? And it turns out that that vector is going to be perpendicular to the other two vectors. But I don't want to talk about that yet. I'm just giving you the magnitude resultant of that. Okay? So, if they're in a perfect situation, if they're 90 degrees from each other, then the result of that is going to give me just a simple product, one times the other. That's the magnitude. Now, if it's not that situation, if they're not at 90 degrees, now let's pretend that instead A is like this, okay? And there's some angle theta that separates A and B, okay, that fill in this space in between the two. Cool? What I need to do is I need to take the component of that A vector that's entirely perpendicular to the B vector. B is on the x-axis in this case. So I'm looking for the y component of that A vector. I'm going to multiply that by the B vector. Now, to do that, I'm going to need to use a little trick. I'm looking for that side of that triangle. Okay? Or if you will, you can pretend that there's another triangle right here. And I have this side of that angle. If I'm trying to determine what that is, what trigonometric function am I going to use? I'm dealing with triangles and one, I have a right angle in there. What trig function would I use in order to determine this side or that side? Okay? Well, the way I always determine trig functions is that there's a simple identity when it comes to sines. Sine theta is equal to theta when it's 10 degrees or less. Okay? So if I think of sine theta is equal to theta when it's 10 degrees or less, and I don't want things to be parallel, okay, so if the angle in between the two is 0, then that means that theta is 0, so sine theta is 0. So the result of this product would be 0. So what that means is that if I have a vector A here multiplied by a vector B here, and I said A crossed with B is equal to AB sine theta, and there is no angle separating the two, then the result is 0. Okay? It has to be 0. That theta angle goes to 0. Put it in your calculator, if you will. Sine 0 is 0. So there's no result here. The product of those two vectors multiplied together is going to be 0. Okay? Because none of it is at 90 degrees to each other. Cool? So the generalized form for cross products, which I'm torn on this decision, either to tell you to just use the generalized form or to use your brain. I mean, I think it's more important that you understand that you're looking for the separation between the two angles, because what happens if they give you that angle instead of that angle? You plug in sine theta and you're going to get a number that doesn't work for you. It's not going to be the right result. But we're not going to worry about that. So the cross product of two vectors, A cross B, the generalized form that we're going to use is going to be A, B, sine theta. Now all I'm doing is putting the magnitude up there. I'm not putting any vector notation on any of this. Just have the vector notation over here, but not over here. This just gives me the size. The direction of that resulting vector, the product vector, has to be perpendicular to the other two. Okay? So if you're looking at this diagram, I'm going to redraw it so everything is at right angles. If you're looking at this diagram of A and B, you're looking at creating a third vector that's perpendicular to those two vectors. Okay? So this one's on the Y, this one's on the X. That third vector has to be on the Z. Has to either be coming out at you, creating a 90 degree here and a 90 degree here, or it has to be going away from you. Okay? So when you're dealing with a cross product, the resulting, I keep using the word resulting, and that's summations. The product vector that you end up with has to be perpendicular to the other two vectors. So AB has to be either this way or that way. Now, how do we determine what direction that is? Well, here's a really interesting thing. Use your right hand. I always carry a marker in my right hand when I'm doing the right hand roll, because that way I have a hell of a hard time keeping track of my right and the left. I actually broke my thumb when I was a kid, my left hand, and that's the way I keep track of it nowadays. A and B, okay? So this is how it's done. Take your hand and put it in the direction of A. A is pointing this way in this vector, so I'm going to take my hand and I'm going to point it this way. Okay? Cool, so I got my hand pointing in that direction. Then you're going to take your fingers, you're going to bend them at a 90 degree towards the direction of B. Okay? So I'm going to have to move A to B. Okay, here's A to B. The thumb points in the direction of the last vector. Okay? So in this case, A, B, Z goes into the board. Okay? That goes into the board. So if you're ever asked what's the product of it and the direction, that's entirely how you do it. A, B, into the board. Got it? That's the right-hand rule. I never thought the right-hand rule was very difficult, but I've read posts online that people complain about it. Put your hand in the direction of A, curl your fingers into the direction of the other vector. So A, B, your thumb is the result. Now, you're going to have to remember this when dealing with the Lorentz force, which is a force on a moving charge in a magnetic field. Don't forget charges carry signs. If you're dealing with electrons, you don't go A, you go A, because it's a negative number. Okay? Cool? Cross products. Last one is a dot product.